Welcome to the stoichiometry video review. The first problem or definition is define stoichiometry, and we have defined that as the mass relationships of elements and compounds and the mass relationship between reactants and products in the balanced equation. This second part is what we've been doing in class, is we've been balancing equations and then figuring out the relationships between products and reactants or reactants and other reactants. So that is our first definition. Question 2 says, what do coefficients represent in the chemical equation? So I've given you an example of a chemical equation here. We have the synthesis of water, and the coefficients, which are the big numbers that I have underlined, represent the number of moles of reactants and products. So for this particular equation, we would have 2 moles of hydrogen, 1 mole of oxygen, and it would produce 2 moles of water. Number 3, how does the law of conservation of mass apply to chemical equations? And the reason it applies is that we must have the same number of atoms and the same type on both sides of the equations. So I use this same example. I have 2 times 2 is 4 hydrogen, 2 times 2 is 4 hydrogen, and then I have 2 oxygen, and then this 2 and that 2 is 2 oxygen on the other side. So that means the law of conservation of mass has been satisfied. Number 4, what units are represented by the coefficients in the chemical equation? And that is moles. And so in this equation here, we would have 4 moles of aluminum, 3 moles of oxygen, and 2 moles of aluminum oxide. So the units of molar mass is grams per 1 mole, or oftentimes we write it G per mol. And remember, the number always goes with the gram, and it's always per 1 mole. I don't care if there's a number in front of the compound. The coefficient never goes with the molar mass. It's always grams per 1 mole, and that's a mistake that a lot of people I see still making. Always 1 mole with the gram. Always, always, always. What is the limiting reagent or reactant? Those are both words that can be used interchangeably. And what it is the reagent or reactant that limits how much product can be produced. And that is because it will be used up first. And so once it runs out, we can't keep making product. And so it's considered to be the limiting reactant. Okay, the example we used in class is if I was wanting to make a bunch of cookies and I only had 3 eggs, then I would run out of the eggs first, so I could only make as many cookies as my eggs would allow. So the opposite of limiting reactant is the excess reactant or reagent, and it is the leftover reactant or reagent that is not used up in the reaction. And so, of course, when we're doing our theoretical yields and we're doing a limiting reactant problem, it'll be the one that produces the higher amount because you would run out of the limiting reactant first, so you would have a lot of this left over. Here's the equation for percent yield. Remember, it's actual yield on the top divided by the theoretical yield times 100, and that equals a percent yield. And you need to remember that the actual is what your experiment produces. It means what you go and test experimentally. And I just realized I spelled experiment wrong. That E is not supposed to be there. And then the theoretical, of course, is what you have been calculating in the stoichiometry problem. So the percent yield tells us what percentage did you get that you should have. And of course, the higher the percentage, the better the yield. Now, in our lab, several of us got more than 100%, but that is very unusual. That means we did something wrong. But in real life, you're not supposed to get more than 100%. Number 9 is actual or theoretical yield calculated through a stoichiometry problem. And we more or less answered that last slide, but let's go ahead and tell that the theoretical yield is what is calculated in the stoichiometry problem. So we calculate theoretical, we have to go produce or actually do the experiment to get the actual. Okay, this slide has 10, 11, and 12. Number 10, 1 mole is equal to 6.02 times 10 to the 23rd molecules or atoms. Remember, if we're talking about compounds, we say molecules. If we're talking about elements, that's where we use the word atoms, but it's the same number. Number 11, 1 mole is equal to 22.4 liters at STP conditions. So we're only talking about gases there. So gases only, not if we're talking about liquids. And then number 12, the molar mass is calculated from the periodic table. Remember, we get it from the atomic mass. So an example is 1 mole of NaCl is 58.44 grams of NaCl. So the way that we did that is we got the atomic mass of sodium and we added it to the atomic mass of chlorine. And when we added that up, we had 58.44 grams per mole. All right, let's get busy starting to work the problems. Remember, I'm highly encouraging you to pause the video and work the problems yourself and then check to see if you got my answer. Okay, so pause it at this time and work the problem yourself. Okay, so when I read this problem, I want to notice that it said a reaction that has been calculated to form 40 grams. So if it's forming it and it calculated it, that's going to be your theoretical yield of calcium chloride. It actually produced 36 grams. So that's going to be your actual yield. And then it wants to know what is the percent yield. So we're going to use that formula, actual over theoretical times 100. So when we plug those numbers in, we should get 90.0%. Number 14, how many liters of hydrogen are required to react completely with 2.4 liters of chlorine to form hydrogen chloride? So here's where we pause the video and work the problem and then come back and see if you get it correct. So hopefully you got 2.4 liters of hydrogen. But let's look at the problem in case you didn't. If you did get it, go ahead and skip to the next slide because you're on the right track. But if not, let's talk about it a little bit. So first things we want to do is see what we're looking for and what we've got. So we are looking for liters of hydrogen because that's what it asked. And so I went ahead and jotted that down underneath, question mark, liters of hydrogen. And then of course we're starting with the 2.4 liters of chlorine. So again, I jot that down under the balanced equation. And then we always start with our given. So we start here. Because we have liters, we're not going to use molar mass here. We're going to use our 22.4 liters per mole of any gas. So that's going to go out on the bottom. And of course, our liters end up canceling out. And so then that means we've converted to moles. So now we're in moles. So our next step was to go to our mole ratio. So I do 1 mole of chlorine. I'm trying to go to hydrogen. So I do 1 mole of hydrogen on the top. And then, of course, the moles of chlorine cancel out. And then lastly, I am in moles of chlorine, but it wants moles of hydrogen, but it wants liters of hydrogen. So again, I use that 22.4 liters of hydrogen per mole. And remember, that's for any gas. And then my last step would be to cancel out the moles of hydrogen. So now I'm left with that final unit that it's asking for. So I'm ready to do my calculations. And so this is where you have your choice of how you want to calculate that. But we need to multiply things on the top and divide by things on the bottom. And when you do that, you should get 2.4 liters. Number 15, how many liters of oxygen at STP are produced when 14 grams of potassium chlorite, that should be chlorate, are decomposed? So pause the video and try to work this problem. Alrighty, how did we do? 3.84 liters of oxygen should be your answer. If you were able to get that answer, then move on to the next slide. If you were not, let's take a few minutes to look at where you might have been making a mistake, or if you got a wrong molar mass, or things like that. One of the things that I want you to make note of, because I'm still catching people doing this is always grams per 1 mole. And this is 22.4 liters per 1 mole. I know that there's these numbers in front of them, and the tendency is to want to take your molar mass and multiply it by 2. But this 2 is taken care of right here. Okay? This 3 is taken care of right here. So that's why we don't want to take the molar mass or anything else and make it grams per 2 moles or grams per 3 moles, because we're taking care of those in those mole ratios right there. So always grams per 1 mole and liters per 1 mole. All right, question 16. I'll let you read it and work it out and then come back and see if you got the answer right. Alrighty, how'd you do? Hopefully you got 218 grams of oxygen. If you got that, move on to the next slide. If you didn't, we need to spend a few minutes looking over what we did wrong. So compare your work to my work and see where you made the disconnect. If I had to guess, most likely I'm going to guess, check your molar mass for oxygen. Because a lot of kids want to put 16 there, but remember oxygen is Brinkoff, so this O2 right here means that we have to add 2 of them. And then of course make sure your units all canceled out like we did here, and then if not, cross out your work and replay the video and rework your problem and see if you get it right the second time. Okay, here we go with question 17. Pause it and work it. All right, hopefully we got 150 grams. We needed 3 significant figures in our answer. So because we needed 3 in our answer, we had to put this little decimal right here so that we would get 150 grams. So that's why that decimal is there. Again, check your answer. If you got it right, move on. If not, spend a few minutes comparing your work to my work. Again, if you are just slightly off, go ahead and check that molar mass right there of hydrogen. Because of this little 2 right here, remember we've got to double the molar mass of hydrogen. All right, so let's move on to the next one. Okay, here's what should be problem 18, but it's renumbered 12 for some reason on your review. So here we go. Pause it and work it and compare. All right, hopefully you're starting to get these right if you haven't been already. So just go ahead and compare your answer. You should have gotten 35.4 grams of nitrogen trioxide. If you did, move on. If you didn't, let's spend some time looking at your work compared to my work. Again, hopefully by now you're realizing that you needed to double that nitrogen because of that 2 right there. So you used 28.02. Okay, so let's move on to the last 2 problems. All right, next one. What is the limiting reagent when you have 46 grams reacting with 62 grams? So, of course, when we see what is the limiting reagent, we are going to need to calculate which one's going to produce the smallest amount. So we're going to calculate in terms of our product of NaCl. So let's pause it and work with both reactants and solve for sodium chloride. Okay, here we go. So when you calculated for 46 grams of sodium, you should have gotten 117 grams of sodium chloride. And when you calculated with the 62 grams of chlorine, you should have got 102 grams of sodium chloride, which is obviously the smallest answer. So that's the one we would box. So the most product we could produce would be 102 grams of sodium chloride, which is also going to be our theoretical yield that we're going to use in the last problem. And then, of course, since chlorine was the one that gave us that smallest theoretical yield, chlorine would be your limiting reagent or your reactant, whichever word you prefer. All right, last problem of the review. Let's go ahead and work this really simple, easy one. From the previous problem, we got 102 grams. So pause it and get your percent yield. All right, how'd you do on the last problem? Hopefully you got 86% yield. If you're still struggling, you might want to replay the video or replay the other stoichiometry tutorial video that is still on the Moodle. If you are done, then stay tuned for the next jokes. If not, hit replay. Okay, here we go. Joke time. First one. Why can't a bicycle stand by itself? Because it's too tired. Next one. What does a clock do when it's hungry? It goes back 4 seconds. And then yesterday I accidentally swallowed food coloring. The doctor says I'm going to be okay, but I feel like I died a little bit inside. All right, good luck on the test, guys.